Alright, in my previous video, hopefully I was successful in berating it into your mind that related rates problems were always going to take the derivative of stuff with respect to t. So like dv dt, dl dt, don't worry, I'm not going to go through 20 of these again, but point is, we're locked into that, right? So if you didn't watch that video, please go back and get brainwashed before you watch this one, because that stuff's really important basics for this class. Anyway, so now we're going to get into some actual problems. Now there's two types. Usually what they'll always start you with is some very basic problems that aren't really real world examples. It's not going to talk about gas tanks or balloons. It'll just say a square is growing at a rate of whatever. Or it'll just talk about geometric shapes. So that's what this video is going to be about, is the more basic ones. And if you're in an easier class, or like an calculus for economics, or calculus for business, or calculus for whatever, then you might never get into the harder problems, because they definitely, depending on how hard your teacher is, it really depends on how hard the problems ultimately get. But if you're in AP, you'll definitely want to do this, and then all the videos in this chapter. Alright, so right now we're just going to look at some basic ones. So strategy summary, don't worry if you don't quite get what this means right now. We're going to get lots of practice in a second. So the first thing is just write down your givens. And just like I've always advocated in all my videos, you kind of want to be really organized in your process. And in these ones, that's going to include writing down the given information really specifically. Then we're going to pick a formula, like the volume or area or Pythagorean or something, that we'll want to take the derivative of. And we'll get it in terms of the letters we need, because sometimes they'll give you information in radius, but then ask for information in diameters or something, so you'll have to be able to convert between radius and circumference and stuff. And then take the derivative with respect to t, and plug everything in, and we'll be done. All right, so let's take a look at that. What is that, 1, 2, 3, 4, 5 steps? Never really counted, but sounds about right. All right, so your most basic problems are just going to involve a simple geometric formula. So here we've got a growing circle. So that makes sense. The circle's getting bigger. It's changing, right? It's getting bigger. It's changing in size. It's changing in radius. Its radius is increasing at 3 centimeters per second. So here's what I mean about writing down the given information. And we practiced this in the previous video a little bit, but the radius is increasing at 3 centimeters per second. So that means that dr dt, the rate of change of the radius, is 3 centimeters per second. Now we could have not written this down and just moved on with the problem, but then once we get to the end of the problem, we'd be looking back and seeing, oh, where's that information? And sometimes what you write down in front will actually affect how you do the problem. So how fast is the area changing? So they want to know dA dt. And for stuff you don't know and what they're asking for, I would put a question mark just to remind me that, hey, this is the letter I ultimately want to solve for. How fast is the area changing when the circle has a radius of 12 centimeters? So they're going to say that r equals 12 centimeters at the point we're talking about. Now this really matters because as the circle, when it first starts growing, you notice they say that the radius is growing at a steady rate, right? So it's getting sort of wider and bigger around all the time. But in that first little bit of growth, it's only going from here to here, but like talk to me in an hour and this thing's going from 1 kilometer to 1.01 kilometers in that second, and obviously the area is changing a lot faster then. So what we're going to do is they've asked for dA dt, which means I need an equation with an a in it. Because remember, we're picking a formula that we're going to take the derivative of. So if you want a dA dt to solve for, you better start out with an a that you can take the derivative of to get a dA dt. They want to know how fast the area is changing when the circle has a radius of 12. So area is a great place to start. They're asking for rate of change of area, so I'm just going to do the area of a circle, which is pi r squared. Now you notice this does not have a dr dt or a dA dt yet, but that's because we haven't taken the derivative. So at this point, once you've picked your formula, all you do is take the derivative of this with respect to t. And you've got to use the implicit method where derivative of a isn't just 1, it's 1 because there's nothing out front, so it's basically an imaginary 1 there. Derivative of area is dA dt. And then pi r squared, pi is just a constant, so we leave it. Derivative of r squared is 2r, but times dr dt. Now dr dt, really important, but it's just like when we did implicit differentiation, and the derivative of y was not just 1, it was dy dx, and that's because we were taking the derivative with respect to x in those implicit differentiation problems. But in this one, we're taking the derivative of everything with respect to t. So that's why we're getting dt's downstairs all the time. But as I explained in the previous video, that's because we want units of time, like 3 centimeters per second. All right, so now we want dAdt, and we've got that. So I think we can just plug and chug at this point, because we want to know what dAdt equals when r, so we'll just plug in for r right here. We'll plug in the 12. And then drdt, they told us, is 3. So if we multiply all that together, we get 72 pi. And that is the answer. So you can see how, in a way, if I wasn't talking so much, all we would have done was said, oh, area of a circle, no brainer, write down a equals pi r squared. Then you take the derivative of it without even really thinking, because that's what you always do in related rates. And then we'll start plugging and chugging and plugging in to get the thing we want to solve for. All right, very similar problem, only this time I'm going to do volume of a box, or specifically a cube. Now whenever they use the word cube, that means a box that's length, width, and height are identical. I know most people that'll make a lot of sense, but sometimes students say, oh, well, you can't assume that. But actually the definition of a cube is that it's the same dimensions in all directions. All right, so a cube's expanding. How fast is the volume changing? So they want to know dV dt, how fast is the volume changing, when its edge length is 5 centimeters. So what should we call edge length? Maybe x is 5 centimeters. And the edges are growing at 2 centimeters per second. So what variable would that be? That would be the rate of change of x. Would be how fast the edge length is growing. It's going to be 2 centimeters per second. All right, so at this point we have enough information to proceed. They're asking for dV dt, which means I need to be using the volume formula. And what is the volume of a cube? Well, it's just those 3 edges multiplied together, so x cubed. All right, so now there's a piece of cake. Now we have the formula we want to take the derivative of. All we do is just take the derivative of it with respect to t, the whole thing. So on the left we get dV dt, and on the right we get 2x squared. Or do we? What did I forget? There's this, if I went to plug in right now, it's like I would plug in 5 for x, so want to plug in 5 for x, but then where am I going to plug in dx dt? That was some information they gave to me that I didn't use. Uh-oh. Must be that I forgot my dx dt, because whenever I take the derivative of any letter, any variable at all, in any one of these formulas in this chapter, we've got to put that variable, dx dt, dv dt, whatever. The d whatever, dt, has got to go, with that term also. And that's what I left out. So that's one big reason that we are always going to write our given information before we do the derivative, is because I want you to always double check at the end of the problem. If you haven't used every number they gave you, there's a really good chance that you've left off a dx dt or dv dt or whatever. As these problems get nastier and longer, you'll end up with more and more terms and stuff, so it gets easier to forget one. But now that we've put it where it belongs, remember that, now we just plug it in. And we get 150. All right, what are the units on this? The rate of change of the volumes. That's going to be centimeters cubed per second. All right, sometimes in science, teachers will make you carry through units on every single number. If I were you, I would just get in the habit of thinking about what should the units be, and then just pick them. So if you know that volume is, rate of change of volume is going to be the units of volume, which are centimeters cubed in this case, because we have centimeters as our length, and then over the time units in the problem, which in this case was seconds, but it could have been minutes or hours or years, in which case you would have put minutes or hours or years downstairs right here instead of seconds. All right, good stuff. So now you hopefully see why we write down information ahead of time. All right, a triangle is getting longer but not taller. Now the key word here is right triangle, and that's going to be making us think, hey, maybe this is SOHCAHTOA, maybe this is Pythagorean. Those are the two things you're going to have in your quiver. The first two arrows out of your quiver, and the ones that will work almost all the time with triangle problems, are SOHCAHTOA, and although not even SOHCAHTOA, Pythagorean's almost all of them. Anytime you're talking about side length, it's likely to be Pythagorean. But we're not sure of that yet, so let's just go ahead and write down some given information. So they said the triangle's getting longer but not taller. So it must have a height of 5 that's constant. We haven't written down the length, but let's just give it a name like L for length of that side. Alright, so it's getting longer at a rate of 9 meters per second. So now that I've named it L, that means I can write down that the given information that dl dt equals 9 meters per second. How fast is the hypotenuse growing? Oh, so I need a letter to represent hypotenuse. Maybe we'll call that h for hypotenuse. So they're asking for dh dt, question mark, when the bottom side is 12 meters long. Alright, so telling us that at the time that L equals 12 meters, how fast is the hypotenuse growing? Now you'll notice we're talking about nothing but side lengths. We're not talking about angles. They haven't given us any angles. They're not asking for an angle. So chances are, those are all the tip-offs to this Pythagorean, which is kind of what we probably thought would be happening anyway. So let's just write down Pythagorean, but of course we'll write it down not with the usual A, B, C, but just with the 3 letters we're working with. So on this triangle, 5 squared plus L squared equals H squared. And the thing that's on by itself on the right of Pythagorean is always the hypotenuse, like always, always, always. Because that obviously has to be the longest thing. For 2 things to add up to another thing, that other thing, the thing on the right, must be the biggest one of them. And that's why the hypotenuse is always by itself. Alright, so once we have a formula with related rates problems, the next step is always to take the derivative of it. So we're just going to differentiate this whole thing with respect to t. Derivative of 25 is 0. Derivative of 2L, or L squared rather, would be 2L times dl dt. And that's going to equal 2h dh dt. Alright, so now we have a bunch of letters, and the one we're solving for is dh dt. That's what they asked for, right? That's the one I got the question mark next to. So I need to get dh dt by itself. So I'll divide both sides by 2h. That'll cancel that. That'll cancel that. So I'll end up with dh dt, just flip the order here, equals L over h times dl dt. Alright, so now I just need to plug in the given information because the thing I want is right here by itself. Once I plug in everything for these letters, other numbers, I'll just get a number out. So what is L? Alright, well we said L equals 12. So you can see this is where it's really nice that we wrote down everything ahead of time. L equals 12. H. Oh, we don't know H. Let's go back. I don't think we didn't write it down. I don't think it's up here. So what is hypotenuse when L equals 12? Well, we can actually use Pythagorean, right? Because we have this formula, the Pythagorean formula on this triangle. And also just because we've, at this point you've probably studied for the SAT at least once, so you remember that 5, 12, 13 is a pretty common right triangle. And you can work that out with Pythagorean. Same thing would happen. So we got a 5, 12, 13. So that means that when L equals 12, H equals 13. So that's what we're going to plug in right here for H. And dl dt we have is 9 meters per second. Alright, so when we plug all that in, we get 8.3. Or obviously, I guess you could just multiply it out and leave it if you're not allowed to use calculators or something. Alright, so that's a Pythagorean problem. No big deal, just take the derivative of the whole Pythagorean theorem. In this case, we only had 2 letters left over, but if we had had a 3rd letter, we could have had even more fun stuff to plug in. But we'll get a taste of those more in the triangles. In the next video, we'll have a bunch more triangle and Pythagorean problems. Alright, surface area of a cube. So this is it's kind of an abstract problem. We don't know why this cube is here. We don't know why it's getting smaller. In real life, cubes don't usually shrink very much. Like Rubik's Cubes and things just kind of sit there. So, what is the surface area of a cube? And how fast is it changing? I don't know. Let's see what happens. Alright, so they're saying the cube is shrinking. So that's a little bit interesting. All that means is we'll put a negative sign in front of whatever number it is. So it's shrinking at a rate of 3 centimeters per second. Alright, so the edge length, and I know I wrote this a little bit ambiguously, like does that mean the volume is shrinking or the edge? But since the units are centimeters per second, that means it must be the edge length. So if we call x the length of an edge, then what we're saying is that dx dt, I can draw this little cube real quick. Can I? Alright, so this is an x by x by x cube. So dx dt is negative 3 centimeters per second. And that minus sign doesn't really matter that much, except that the surface area will also be shrinking, and therefore our answer should probably be negative. But it'll turn out that the signs will probably work out and we'll get a negative answer if we just plug in properly using the correct dx dt. All right, so that's how fast the edge length is changing. How fast is the surface area shrinking? So they want to know how fast is I think S is the surface area. How fast is ds dt shrinking when the cube is 9 by 9 by 9? That means obviously when x equals 9, because x is what we're calling our edge length. All right, so here's a bunch of stuff we could plug in. Let's see if it works out, or if there's any letters we'll have to calculate later. So we're going to need a surface area equation. Since they're talking about surface area, we're going to have to use a surface area formula. What's the surface area of the cube? Well, all we have to do is just add up all the squares that make up the cube. So each side is going to be x by x, so it'll have a surface area of x squared. And if you look at a box, it's got 6 sides. So the surface area of a cube is just 6x squared. Now that we've got a formula, take the derivative with respect to t. And ds, the derivative of s is just ds dt equals 6 times derivative of x squared, which is 2x, dx dt. So that's just going to equal 12 x dx dt. All right, so do we have enough letters to plug in for that? We got x and we got dx dt, so I think we're set. So 12 times x, which is 9, times dx dt, which is -3. And just plug that out, and we get -324. All right, and what are the units on that? Well, let's see, it's a surface area, so that'll be units squared, like meters squared or something. But since this one's in centimeters, we're going to go with centimeters squared. Oh, and they're asking how fast it's changing, so that's per second, since seconds are the units in this problem. All right, pretty fun. If your teacher asks for units, and honestly they usually do, then you have to sort of backtrack and put it together. All right, the volume of a sphere. Oh, here we go. Got the volume of a sphere right there. You're gonna have to memorize this one probably, and maybe you did in a previous class like Algebra 2 or something. Volume of a sphere is increasing at a rate of whatever. Because it's the volume of a sphere, it's pretty obvious this is going to be our formula, 4/3 pi r cubed. The volume of the sphere is increasing at a rate of 3 cubic meters per minute. So dV dt equals 3 meters cubed per minute. As it grows, how fast is the radius increasing? dr dt equals question mark when the sphere has a diameter of 7. So d equals 7. All right, so now right away I've already noticed something, and this is something that'll happen in circles. There's a bunch of different ways to tell somebody the size of a circle. They could give you the diameter, or the radius, even the circumference or something wacky like that. So we want to, we want to be using the same letter throughout. So in this case, they're asking for something dr dt, and r is what's in my original formula, but they gave me some information as a diameter. So what I'm going to do is I'm just going to replace this with r equals, diameter is twice the radius. So that means the radius must be 3.5. So I'm just going to replace d equals 7 with radius equals 3.5 because I want to use all radiuses. I want to use r everywhere if I can. All right, so I've got the given information. How fast is the radius increasing when the sphere has a diameter of 7? All right, so we're going to start with v equals 4/3 pi r cubed. And then we'll start taking the derivative of stuff. So derivative of volume is dV dt, 4/3 pi, and then the derivative of r cubed is 3r squared, dr dt, don't want to forget that dr dt, that 3 cancels that, which is nice. Let's see, so we got dV dt equals 4 pi r squared times dr dt. All right, so now that we've taken the derivative, let's see what our thing's asking for. Oh, we're asking for the derivative of radius, so dr dt. So that means this thing right here is what I want, and all this other stuff, I need to get rid of this. So I'm going to divide both sides by 4 pi r squared. So I'll get dV dt over 4 pi r squared on the left is equal to dr dt. And at this point, I can just plug in. So my dV dt that was given to me is 3. Then I got 4 pi, and r squared is just going to be 3.5 squared. And when I plugged all that in using my calculator, I got 0.0024. And what are our units? Well, let's see. There's the rate of change of radius, so we want a distance per unit time. Looks like we got meters per minute. All right, not the craziest problem. This volume formula is awkward because it has a 4/3 in it. It's got a pi and stuff, but not too bad to use. As always, all we do is figure out a formula and then take the derivative of it with respect to t. All right, so strategy formula is the same slide I showed you at the beginning, but hopefully it makes more sense now. First, we're going to write down all our givens. If they give you a length, write down a length, but if they give you the rate of change of something, write it in that d whatever over dt form, dl dt, dx dt, dv dt, whatever. Like really give your variables names and write them down in that derivative variable form so that you know, so that you'll be able to spot it real quick when you want to plug in to the problem. And also give you a lot of practice, because the hardest part about these problems is taking those words like rate of change or whatever, or something is growing by whatever at whatever rate, and turning that into variables to plug in. Then all we have to do is come up with a formula which has kind of similar letters to what we're looking at. So if it's an area problem, use an area formula. If it's volume, use a volume formula. Double check it has the right letters. So like on that last one, we switched diameter to radius in order to solve things out. In some problems, it'll be a little bit trickier than that. We'll see some in the later videos. Sometimes we'll have to do trickier things like swap out circumference for radius or radius for circumference. You know, something a little bit juicier than just going from radius to diameter, which is pretty simple. Take the derivative with respect to t. That's the, it's in a way it's the easy part, but it's also hard because it's so easy to forget just one of your, you know, if you forget dr dt next to that r squared, all of a sudden the answer is going to be wrong. And then just plug and chug and drill it out on your calculator. All right, so there you go. That's the, those were what I consider abstract problems, because they're not talking about a real world situation. They just said a cube, a circle, a sphere. They didn't tell us it was a balloon, or it was cement filling a mold, or it was ice cream melting on the ground or anything. So in the next videos, we'll get into that kind of stuff, where it's a more real world situation. But you'll see the process is actually pretty much identical to what we were just doing. It'd just be a tiny bit trickier to figure out the geometry.